A superatomic semiconductor has achieved record-breaking speed. Scientists are currently in pursuit of improved semiconductors. In an article for Science, a group of chemists from Columbia University, led by Jack Tuliag, a PhD candidate working alongside chemistry professor Milan Delors, outlined their discovery of a superatomic compound named Re6C8Cl2. This material is the swiftest and most effective semiconductor known to date. The building blocks of modern technology, such as computers, cell phones, and other electronic devices that we rely on every day, are made possible by semiconductors, with silicon being the most notable. Despite their widespread use, semiconductors possess certain limitations. All materials possess an atomic structure that vibrates, generating quantum particles known as phonons. These phonons, in turn, cause particles that carry energy and information through electronic devices, such as electrons or electron-hole pairs called excitons, to scatter in mere nanometers and femtoseconds. As a result, energy is lost in the form of heat, and information transfer is restricted by a speed limit. A team of chemists at Columbia University, led by PhD student Jack Tuliag and chemistry professor Milan Delors, has announced a breakthrough discovery in the field of semiconductors. The search for superior alternatives has been ongoing, and their findings, published in Science, reveal a superatomic substance known as Re6C8Cl2 to be the most rapid and effective semiconductor to date. Excitons in Re6C8Cl2, a material of interest to researchers, exhibit a unique behavior when they interact with phonons. Unlike other materials where excitons scatter upon contact with phonons, in Re6C8Cl2, excitons bind with phonons to form acoustic exciton polarons, a new type of quasi-particle. While polarons are commonplace in various materials, the acoustic exciton polarons in Re6C8Cl2 possess a distinctive characteristic. They demonstrate ballistic flow without scattering. This property has the potential to lead to faster and more efficient devices in the future. According to the team's experiments, there was a significant increase in the speed of acoustic exciton polarons in Re6C8Cl2, which were able to traverse several microns of the sample in less than a nanosecond, twice as fast as electrons in silicon. Exciton polarons can last up to 11 nanoseconds, leading the team to believe that they can cover over 25 micrometers at once. Since these quasi-particles are governed by light instead of an electrical current or gating, theoretical devices using them have the potential to process data in femtoseconds, which is 6 orders of magnitude faster than current gigahertz electronics, and all at room temperature. According to Delors, when it comes to the transportation of energy, Re6C8Cl2 is presently the most effective semiconductor that we are aware of. In the laboratory of collaborator Xavier Roy, a superatomic semiconductor known as Re6C8Cl2 was created. These superatoms are composed of clusters of atoms that are bonded together, and they exhibit the properties of a single, distinct atom. However, they possess different properties than the elements used in their construction. Synthesizing superatoms is a specialty of the Roy Lab, and they are a key focus of Columbia's NSF-funded Material Research Science and Engineering Center on precision-assembled quantum materials. Delors has a particular interest in controlling and manipulating the transport of energy through unique materials like superatoms that are developed at Columbia. To achieve this, the team employs the construction of super-resolution imaging tools which are capable of capturing movement of particles at ultra-small and ultra-fast scales. Initially, Tuliag's objective for bringing Re6C8Cl2 into the laboratory wasn't to explore the development of a superior semiconductor. Rather, it was to scrutinize the capacity of the lab's microscopes using a substance that, theoretically, should not have exhibited any form of conductivity. According to Delors, the outcome was entirely contrary to their expectations. Instead of observing sluggish movement, they witnessed the most rapid movement they had ever encountered. During the following 2 years, Tuliag and his colleagues from the Delors group concentrated on unraveling the mystery of Re6C8Cl2's extraordinary properties. One of their achievements was the creation of a sophisticated microscope with unparalleled spatial and temporal accuracy, which was capable of capturing images of polarons as they emerged and traveled within the substance. Meanwhile, theoretical chemist Petra Shai, who was pursuing her PhD under Timothy Birkelbach's guidance, devised a quantum mechanical model that could account for the observed phenomena. According to Delors, the new quasi-particles achieve their impressive speed by taking the slow and steady approach. This is similar to the fable of the tortoise and the hare. Silicon is a highly sought-after semiconductor due to its electrons' ability to move rapidly through it. However, these electrons tend to bounce around and not travel very far in the end. In contrast, excitons found in Re6C8Cl2 are quite sluggish, but their slow speed allows them to combine with acoustic phonons that are also moving slowly. This results in the development of heavy quasi-particles that, like the tortoise, move steadily and gradually. Acoustic exciton polarons present in Re6C8Cl2 move faster than silicon electrons because no other phonons impede their progress. At Columbia, a multitude of quantum materials are being investigated, including Re6C8Cl2. This substance, like many others, can be peeled into thin layers of atoms, making it a prime candidate for combination with other analogous materials in the pursuit of distinctive properties. Nevertheless, Re6C8Cl2 is improbable to be used in any commercial product due to the exorbitant expense of its first component, rhenium, which is one of the most uncommon elements on the planet. Armed with the new theory developed by the Birkelbach group and the advanced imaging technique pioneered by Tulliag and the Delors group to monitor the creation and migration of polarons, the team is now poised to discover other potential superatomic candidates that could outpace Re6C8Cl2. According to Delors, this material is the solitary substance that has exhibited ballistic exciton transport at room temperature. However, there may be other materials that can exhibit this behavior that have not been considered yet. Delors predicts that there are many other 2D semiconductor materials, including superatomic materials, that may have properties conducive to acoustic polaron development. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.